All right, the last thing we're going to look at for triangle proofs right now is coordinate proofs. So this is not a major topic. It is in the workbook, so I thought I'd make a video to go over it. But basically what we're doing in coordinate proofs is taking triangles, putting them on a coordinate plane, and then using things that we know about distance, midpoint, and things like that in order to write proofs. These aren't going to be two-column proofs because we don't have like the statements and reasons that go with the other proofs we've been doing. These are more informal proofs or like paragraph proof style. So let me go through a little bit with you. I think this is coordinate proofs because that's the topic. Coordinate proofs use figures in the coordinate plane. The first step is placing the figure on the plane. So we're going to use the origin as a starting point. So kind of like when we looked at geometry from an engineering perspective and through a computer-aided design perspective, the origin is like our anchor spot that lets us just kind of place something so that it can't slide freely around the plane. So the origin is always a nice spot to anchor onto because the coordinates 0, 0 are very convenient. We're going to place a side of the triangle on an axis. So if we have a triangle, we don't want to draw it like this. We want to have one of those sides flat against an axis. Again, I think of that like engineering. If I'm setting up something for 3D printing, I want it to be flat against the print bed, so I want my shape to have a flat face laying on the ground to where it's going to print as it builds up. Keep the triangle within the first quadrant if possible. So we like positive numbers. Positive numbers are easier to work with, so if it can't stay within the first quadrant, that's okay, but it'll make life easier if we keep all our numbers positive. And then use numbers? I don't know. I don't actually know what goes there. I don't know. Anyways, I'm not too worried about it. So place an isosceles right triangle in a coordinate plane, then find the length of the hypotenuse and the coordinates of its midpoint. So following these kind of directions, we have a couple options. We're going to put a vertex at the origin, and then we're going to put a side along the x-axis. That means we could draw the triangle like this, but if we're going to put one side along an axis, why not put two sides along an axis? It would be even nicer. So I'm going to draw the triangle. It says isosceles, but it doesn't say how big, so we're just going to make a generic sized isosceles right triangle. We have our 90-degree corner. We have two equal legs that are both in the way. I drew it 6, but they don't have to be 6. It says find the length of the hypotenuse and the coordinates of its midpoint. So we want the length of the hypotenuse and this point at the midpoint of the hypotenuse. So I can clearly see from my coordinates with a side length of 6 that my midpoint is at 3, 3. But that's not really like a proof, right? So we want to write this as a more generalized statement of how to find that based on any side length. So rather than just side length 6, let's say we have side length x, right? So we have this is x and this is x. So now we could say that the midpoint is at, I guess using the midpoint formula, you could say x minus 0 over 2, comma, right? Because this is point x0. I don't know if we need to say that explicitly since it's on the picture, or if we need to say, I think that's fine. And we know 0, 0 is always our origin, right? If the legs get longer, they're going to grow along the right and up directions. So we have this point is x0, this point is 0, 0, and this point is 0, x. So that means that our difference of x's, our average of our x's, is x minus 0 over 2. Our average of our y's is also x minus 0 over 2. So the midpoint is at x over 2 comma x over 2. So basically it's at half of the leg length in the x and y direction. And no matter what shape the triangle changes to, that'll always be true. So not much of a proof, but it kind of brings in the midpoint formula and this generalized isosceles right triangle to give us a rule about how that would work. And then for the length, we're going to need the distance formula. So I guess we're going to need, what is it? x2 minus x1 squared plus y2 minus y1 squared. And then we need to plug in the things we know. So this is the length of our hypotenuse. So the length is the square root of x minus 0. I did that one above wrong. I just realized this should be x plus 0. We're doing an average there. It doesn't actually change it since it's 0, but it should be x plus 0 for midpoint. Okay, so we have x minus 0 squared plus x minus 0 squared. So we get the square root of x squared plus x squared, which is the square root of 2x squared. So factoring that, we can take out an x. So we get the length equals x times the square root of 2. And for those that are familiar with isosceles right triangles or with squares, you should probably already know that the diagonal of a square or the hypotenuse of a 45, 45, 90 right triangle is the side length times the square root of 2. And we'll be doing more with that in special right triangles a little bit later. So this is kind of a proof of that general concept if you need a way to like show it. All right, next thing we're gonna look at is here. Now we'll skip that, that's easy enough. Let's try to write a coordinate proof for something that looks more like given as a proof. So it says, write a coordinate proof to show that a line segment joining the midpoints of two sides of a triangle is parallel to the third side. So this one sounds fairly complicated. I actually haven't looked at this before myself, so if you want to pause and try it on your own, go ahead. You know that we're going to need to come up, it says prove something is parallel. So we know we need a converse of some transversal rule. So we're looking for converse of alternate interior angles or alternate exterior angles or corresponding angles or consecutive interior angles. We need one of those converses to come up with this conclusion. So we need to find a strategy that's going to get us to that. So we have triangle ABC. We have S as the midpoint, T is the midpoint. So we found in the last section that the midpoint would also be the midpoint of the coordinate distance. So we could say that S is at 2b plus 0 over 2, so that's B, and it's at 2c plus 0 over 2, which would be C. So S is at B comma C. Then we have T is at, it's halfway between this one and this one. So T is at 2b plus 2a over 2, comma, 2c plus 0 over 2, which is just C. So that means they're at the same height, so that seems like a positive step in the right direction. So if C and C are at the same height, that's going to be helpful probably. We can simplify this to be just B plus A comma C. So this is all midpoint coordinates. Let's see, what can we do next? How do we get information about our angles? Maybe it's that we need to prove the two triangles are similar. So we know similar triangles must share all three angles in common. So that would mean angle C is the same for both, angle A is the same as S and B is the same as T. So if we could prove similar triangles, then that would give us a way to talk about the angles. And once we knew that, these two angles being equal would be our corresponding angle postulate that we needed to prove this. So to find out if the triangles are similar, we need them to have all proportional sides. So if we know that the proportion of OC to SC, CB to CT, and OB to ST are all the same proportion, that would tell us the triangles are similar, and that would mean the angles are the same. So let's set up those ratios. We're going to do OC over SC. We're going to do CB over CT. And, oh, that's not O, I guess that's A. I was doing origin. And AB over ST. So we're going to set up these three ratios. AC, I guess we have to do distances for all of those. Maybe. There may be a better way, but that's what I'll do. So AC equals, and we're going to do the square root of 2b, so 2b minus 0 is 2b, squared is 4b squared, plus 2c minus 0 squared is 4c squared. We can divide out a 4, so that would be equal to 2 times the square root of b squared plus c squared. That to me looks very promising because there's a 2, and if we're trying to establish a ratio relationship, if the other one, what went with AC? If SC comes out to be just b plus c squared, that would be a 2-to-1 ratio. So SC is the square root of, so we have 2b minus b, so that's b squared, plus 2c minus c, that'll be c squared. So AC over SC is a ratio of 2-to-1. So that's our ratio of those sides. If we do the other sides, CB, the distance would be 2a minus 2b squared. Yeah, okay, that's going to be uglier. Okay, I'm going to write that. 2a minus 2b squared plus 2c minus 0 squared, or 0 minus 2c squared. That'll come out to 4c squared. And then the other one, CT, is going to be the square root of, so t, I'm going to put the coordinates here, was b plus a comma c. So my x distance is 2b minus b plus a, so I distribute that to get minus b minus a squared, plus 2c minus c squared is just 1c squared. Okay, so let's see what we end up with if we simplify here. So this one, we have 2a minus 2b squared. I'm going to do that up here. That's 4a squared minus 4ab, don't know why I wrote plus, minus 4ab plus 4b squared. So that was this parentheses part. So now the nice thing is, just like here, everything has a coefficient of 4. So I can factor out a 2 from all of these 4 terms and bring it out as a 2 in front. So now I'm left with a squared minus ab plus b squared plus c squared. So very ugly, but again, as long as this comes out to be the same as this, we have a ratio of 2-to-1. So let's simplify this one. We have 2b minus b, that's just becomes 1b, because we simplify or collect our like terms. So b minus a squared is b squared minus 2ab, right, because minus ab, yeah, plus a squared plus c squared. So, really close, but I'm missing a 2 on this ab, meaning I probably did something wrong up here. So here we had minus 4ab twice. Yes, this should have been minus 8ab, meaning that when we factored out this 2, we're still left with minus 2ab here. Perfect. So again, we have a ratio of 2 to 1. It's not pretty, but we got it. And then our last one, do we know? We do know how long ST is. Okay, so AB is pretty easy to find the length of because it's just 2A, right? It's along a straight horizontal line, so we don't need to do the distance formula really. So AB equals 2A. And then we need to find ST as our last one. So ST, we're going to, basically we just subtracted here, right? So we're just going to subtract. So the y distance is 0. The x distance, we went from b plus a to, or from b to b plus a. So the distance between those is just a. So again, we end up with a nice ratio of 2 to 1. So now we could say that triangle SC, or let's do ACB, is similar to, so not congruent to, but similar to triangle SCT. Great. So we have 3 main steps so far. We had midpoint, we established similar triangles and wrote a similar triangle statement. Then, based on similarity, we know that corresponding angles of a similar triangle are congruent. So that, I would need some more paper below here. I'll just go off to the side. So following here, we're going to say that angle S is congruent to angle A, and we know that by similar triangles. And then finally, we could say converse of corresponding angle postulate to prove that the lines are parallel, because we have 2 corresponding angles and they are congruent because the triangles are similar. Again, I don't know if that's how that was intended to be proven. I hadn't looked at this problem ahead of time, but it seems like that's a valid way of approaching it. Not an easy problem, of course, because it has lots of distance formula in it, but it is something that we can prove. Okay, so I think we're going to end there on this. I hope you get the idea of how these proofs work, that they're not 2-column proofs that are formal like the other ones we've been doing. They're more informal proofs where we're kind of just reasoning our way through it. We're using the same kind of logical tools, right? We're still connecting each step to the one before it, but we're not writing it with those kind of vocabulary terms necessarily.